Thank you, Francesca. It's a honor of a lifetime to be elected to membership. Microphone, yes? Higher, closer, all right. It is still a honor of lifetime to be elected to membership of this institution and be part of this event. So what I'd like to do today is to engage you on a topic that brings all of us together with our diversity of minds and endeavors for no lesser stakes than understanding the origin and evolution of our complex universe and our own Milky Way galaxy. So I'm going to expand on some points that have been discussed this morning by Francesca. Let me start by saying I am an astrophysicist by trade, that lonely 1 in 100,000 randomly selected people whose professional interests do not lie on the surface or near the surface of our own planet Earth. Astronomy is one of the oldest disciplines, second perhaps only to medicine. But as astrophysicist, a member of this academy, Martin Rees, once put it, it was probably the first science to do more good than harm. No offense to our colleagues of medicine, with the calendar, the estimate of the Earth-Sun distance, the measurement of the Earth meridian navigation, etc., etc. One of the purposes of astronomy is to understand the birth and evolution of our universe, and here we have an advantage over paleontologists because a telescope is actually a time machine, and astronomy becomes necessarily history. As we heard this morning, light travels at finite speed. We observe distant galaxies not as they are now, but as they were when they emitted radiation that propagated throughout the cosmos, radiation that gets stretched by the expansion of the universe towards longer and longer wavelengths. Effectively, photons are losing energy as they propagate in an expanding universe. Astronomers then can look back in time by studying objects that are progressively further away, and like historians interpret the present in the red light of the past. What you should be seeing here, and maybe you will see, let's see, yes, is one of the deepest and most extraordinary near-infrared images of the universe. This is the JADES origins field observed with the James Webb Space Telescope less than 2 years ago. It shows a small portion of the sky, about 10% of the area of a full moon, in the constellation of Fornax. In this image, this tiny field contains about 100,000 galaxies and captures in a single image about 13.5 billion years of cosmic evolution. The small and red galaxy that you can see in the pullout is the most distant object ever revealed by a telescope. It dates back to when the universe was just 300 million years old, about 2% of its current age, and the light for that galaxy has been redshifted by a factor of 15 or so. So we can only detect it in the infrared. The light emitted by all the sources in that image tells us that when the universe was roughly 2 billion years old, or just 15% of its current age, galaxies had already formed about half of their stellar mass. And because, as we heard this morning, stars convert by nuclear fusion the lightest and most abundant chemical element, hydrogen, into heavier elements such as carbon, oxygen, magnesium, silicon, and iron, the magic of stellar alchemy had already produced those nuclear waste, if you want, that are necessary for the formation of rocky planets such as Earth. If you think carefully what that means, it means a lot of things, but one thing in particular is that planets capable of supporting simple life, like the methanogenic microorganisms that dominated much of the early history of life on Earth, may have formed in the Milky Way 10 to 11 billion years ago, more than 5 billion years before the formation of our own solar system. This seems to me like a remarkable possibility, a point I would like to return towards the end of my presentation. Now, one basic observation about our universe is that we live in an increasingly complex cosmos, one that is constantly changing, creating new structures that then aggregate over time forming bigger and bigger cosmic structure. A universe that emerged from a hot and dense sea of photons and elementary particles, spectacular in some way, but initially uniformly boring. But that, as it cooled down, became more and more interesting, first forming protons and neutrons, then nuclei of helium, and finally, after 400,000 years after the Big Bang, the first atoms of hydrogen. And then, under the relentless action of gravity, the first stars, galaxies, massive black holes, about 300 million years after the Big Bang. So if we then define the complexity of a physical system as the amount of information that is necessary to describe its state and its evolution, the total complexity of the universe has increased enormously compared to the primordial cosmos. And that is why many astrophysical investigations today require the universe on numerical simulations on large supercomputers. So what you are seeing in the background is a multi-billion particle simulation of the formation of the dark matter halo. You went very fast. It's a big file. Of the dark matter halo of our own Milky Way, a simulation we ran at the Barcelona Supercomputer Center more than 15 years ago, but still state-of-the-art today. What you're seeing is the distribution of dark matter in a cubic region of the universe centered on a Milky Way-sized object at the center of that video, which I can see here, but you cannot see there. Maybe you can start this video again. Today, thanks to simulations like this, we know that galaxies form in the densest region of a dark matter cosmic web, at the center of dark matter lumps like those you can see in the video, perhaps. But it's not going because it's sort of too big, and I knew this. My apology. So based on the results of these simulations, we predicted the existence of hundreds of very concentrated dark matter clumps surviving near the solar circle, a lumpiness in the local matter distribution that we argue would boost the dark matter annihilation signal and possibly produce detectable gamma rays. None, unfortunately, has been detected so far. You would know otherwise. But this may be telling us something about the properties of the dark matter particle, and there is still hope. So the evidence for dark matter is compelling. Everything we observe across the electromagnetic spectrum, touch or experience on Earth and in the universe, it's only a small fraction of the matter in the cosmos. So for every particle of ordinary matter, you are familiar with protons, neutrons, electrons, that form us as well as planets, stars, and galaxies, there is more than 5 times as much in terms of mass in the form of a new elementary particle that we never revealed that interacts very weakly with ordinary matter. This dark matter dominates the attractive gravitational force of today's universe. All of our cosmological models require dark matter in order to be self-consistent. Without the extra gravity that dark matter provides, galaxies would not form at sufficient speed in an expanding universe, and we wouldn't be here arguing about the nature of the dark matter particle. Over the course of your lifetime, about 1 milligram of dark matter will pass through your body as if it was not there at all. Yet, if dark matter has some non-zero probability of colliding with ordinary matter, then we will be able to reveal it sooner or later, perhaps with the Xenon NT experiment at the Gran Sasso National Laboratories. So it is dark matter that connects the physics of the extremely small with the astrophysics of the extremely large. There is another observation I'd like to make about our universe, is that we live in an expanding universe, but the expansion is not decelerating, as you would expect in a universe made of matter and radiation, but in fact is surprisingly accelerating. meaning that space is expanding more rapidly today than it was a few billion years ago. In a universe that is mathematically described by general relativity, this phenomenon is explainable only in the presence of a vacuum energy that exists even without matter and permeates all of space in a uniform way. Postulated by Einstein in 1917 in order to stabilize the universe and make it static, and then repudiated as the biggest nonsense of his life, this enigmatic dark energy produces a repulsive gravitational force and is responsible for the accelerated expansion of the cosmos that we observe today. Its existence is one of the most complex and meaningful problems of modern physics. To summarize it, in short, we have not the faintest idea of what dark energy is. But thanks to a multitude of observations and data, we know precisely that in order to accelerate the expansion at the observed rate, 68% of today's universe mass energy content must be in the form of dark energy. So now if you add dark matter to dark energy, the share of matter energy that is of unknown nature rises to 95%. Ordinary matter, it's only 5% of the total. So we are made of precious material, if you want. Our understanding of the genesis and evolution of the universe is one of the great achievements of 20th century science. Our universe can be analyzed from any point of view, the mystical, the philosophical, the scientific. In science, we adopt the slowest and most difficult path. We accept only what is confirmed by experiments or observations. Now, astrophysicists, as I have said, are historians of the universe. But like economists, they are not very good at making predictions. And so I will refrain from making any, and I'm going to conclude this talk with some informed guesswork on a scale that is much smaller than what we've seen today, the scale of our solar neighborhood, a few hundred light years away from the sun. Since the first detection in 1992, over 5,000, nope, not that. Why is this here? All right? Yeah, launch the video. Thanks. That's not it. Oh, well. All right, maybe that's it. Since the first detection in 1992, over 5,000 exoplanets have been found orbiting nearby stars. Using the transit technique shown in the video, in a while though, I'd made it shorter, NASA Kepler space mission has helped identify many Earth-sized rocky planets. So what Kepler does is to measure the flux, with extremely high precision, the flux of a star-planet system. And while a transit of a planet along the line of sight of the stars gives information about the planet's size and orbit, the secondary tiny eclipse that occurs when a planet passes behind the star, causing a decrease, a tiny decrease in total brightness, sets constraints on the thermal emission and reflected light, the albedo if you want, of the exoplanet in question. Of particular interest are terrestrial habitable planets, Earth-sized planets in the habitable zone of their sun-like star. Habitable zone that is defined as the region in which a rocky planet with an Earth-like atmospheric composition can sustain liquid water on its surface. Since the first detection, it is the greenhouse effect that determines the boundary of this habitable zone region. The inner edge is where the greenhouse effect, inner edge closer to the star, is where the greenhouse effect would cause water to boil away, while the outer edge is where the greenhouse effect cannot keep the surface warm enough above freezing. So the basic requirement of surface liquid water is predicated on a subset of the minimum conditions that are needed for the existence of a simple microbial biosphere. Now, it is estimated from Kepler data that the occurrence frequency of habitable planets around Sun-like star is very high, close to 25%. The implication of this number may be astounding, as within the solar neighborhood, 100 parsec away, or if you want 326 light years, there may be as many as 10,000 habitable planets around Sun-like stars. Many of them, as I said at the beginning of this talk, older than our own solar system. Simple life emerged on Earth within the first billion years of its habitable window. Yes. The oldest generally accepted evidence for life on Earth comes from observations of microbial sulfate reduction in the 3.5 billion year old Dresser Formation of Western Australia. So while the probability of abiogenesis on Earth-like exoplanets is of course currently unknown, the high frequency of terrestrial planets in the habitable zone around Sun-like stars invites the question of how often, if at all, simple microbial life may have arisen on other worlds in the past. Now, you can estimate that the closest life harboring, and I'm talking about simple life here, terrestrial planet will be only 65 light years away, which is 20 parsec, which is very close, if microbial life arose as soon as it did on Earth in just 1% of those 10,000 habitable planets in the solar neighborhood. So in the coming decades, advanced space and ground-based observatory like NASA's Habitable World Observatory and European Extremely Large Telescope will allow an unprecedented opportunity to probe the atmospheres and surface of nearby Earth-like planets in the search for possible biosignature. The discovery of extraterrestrial simple life, bacterial life, would still be a landmark moment in the history of science, with implications that would reverberate throughout of all of society. So to understand the scientific and cultural impact of that finding would take, I think, the range of disciplines embraced by this academy and by those in this hall. So in some sense, I'm happy we are in it together, honored to be sharing this time in history and this celebration with all of you. Thank you very much.
Thank you, Piero. Are there questions?
On the first slide, you have shown a plot of brightness toward the wavelengths of light emitted by a galaxy.
Yeah, that was, yes.
What is the physical significance of this jump and about exponential decay at 2 microns?
That's
what does it mean?
Lyman alpha. It's Lyman alpha, which is UV.
Lyman alpha. And
it's
there is an
Lyman
exponential
alpha.
decay.
It's because those photons are absorbed, scattered off the line of sight by neutral gas, intergalactic gas, in between galaxies. So what you're seeing is a UV spectrum of a distant galaxy, which has been redshifted by a factor of 15, and that's why it's 2 microns.
But it's very strange, this jump.
Because it's a line, it's a broad line, it's Lyman alpha, and then the blue wing of Lyman alpha gets absorbed by intergalactic gas because those photons resonate, scatter off the line of sight, and you see a sharp drop. It's what we see in all high redshift sources.